Hello and welcome again. Please subscribe to our channel if you did not subscribe to our channel by clicking subscribe button and bell icon for your personal notifications. If you like the concepts in the video, please kindly press like button. This is a session on in the series of STM32H7. This is a session on STM32H7 memory. First, initially we'll look at embedded flash, and then we will go through FMC and quad SPA eventually. So STM32H7 devices embedded high-speed embedded memories with a dual bank flash memory up to 2 megabytes that can be used for storing programs and data. In this session, we'll go through the key features available for flash memory, and then we'll look into the block diagram of flash memory block. Later on, flash memory architecture, and then we go through memory organization and flash read operations available, flash error code correction and cyclic redundancy check, flash program and erase operations, flash programming sequence, and then write status busy flags and write status busy what you can say user option bytes available, and interrupts for the flash memory. So let's quickly jump onto the thing. The flash memory is organized as 266 bit flash words that can be used for storing both code and data constants. Each word consists of one flash word, that is 8 words or 32 bytes or 256 bits. 10 ECC bits. The STM32H7 series has a flash memory with dual bank organization supporting simultaneous operations. To read or program or erase operations can be executed in parallel to the two banks. So further in the key features, the flash memory supports enhanced security features which can be configured using the option bytes. The readout protection RDP, the sector write protection, and 2 PCROP. One per bank. Execute only memory, which executes only memory. The flash interface allows swapping bank 1 and bank 2 memory mapping. This feature can be used after a firmware upgrade to restart the device on the new firmware after a system reset. The flash interface allows also setting a secure area in each flash bank. The data and programs stored in this area cannot be accessed unless the secure mode is set. The secure area helps isolating secure user code for non-secure application code. Please refer to the specific training about system protections for more details about these protection options. Let's quickly move on to the flash memory block diagram. The figure here shows the flash memory high level block diagram. The flash interface implements a dual AXI bus interface for code or data accesses and an AHB interface to configure the flash memory interface. The AXI interface can request a read or program operation at the same time. Okay. The flash memory is organized as a 266-bit flash words that can be used for storing both the code and data constants. Each word consists of one flash word which is 8 words, 32 bytes or 256 bytes, 10 ECC bits. The flash memory is divided into two independent banks. Each bank is organized as follows. A 1 megabyte flash memory block containing 8 user sectors of 128 kilobytes, 4K flash words in other terms. 128 kilobytes of system flash memory from which the device can boot. This area contains root security services, that is RSS, and the bootloader, which are used respectively for secure or non-secure flash memory programming through one of the following interfaces: USART, USB, or DFU mode. Okay, I2C or I2C, SPI, or Ethernet. The system flash memory is reserved for use by ST Microelectronics. It is programmed by the ST Microelectronics when the device is manufactured, and then protected against spurious program or erase operations. For further details, please refer to an application note AN2606, which will have a title as STM32 microcontroller system flash memory boot mode, available from st.com. 2 kilobytes, that is 64 flash words of user operation bytes for user configuration. This area is available only in bank 1. I repeat, 2 kilobytes of user option bytes for user configuration. This area is available only in bank 1. Unlike user flash memory and system flash memory, it is not mapped to any memory address and can be accessed only through the flash register. So this raises a doubt, like how the memory organization is associated. Here it is. This table describes the flash memory organization that is divided into two banks, which we were talking in just now. Having a main memory block contains 8 sectors of 128 kilobytes each. Each main memory block has system flash block that contains the system memory, which is reserved for use by ST Microelectronics and contains the bootloader. When selected, the device boots in system memory to execute the bootloader. 2 kilobytes, that is 64 flash words of user option for using configuration, which is available only in bank 1. So you can look at the block base addresses and sizes respectively. Have a look at it. Then we will speak about flash read operations. I'll list you the flash read operation. So seeing this memory organization flash interface can be accessed by double word 64 bits. The single word, that is 32 bits, by half word 16 bits, or by bytes, that is 8 bits. The flash interface clock must be enabled and running when reading information from flash memory. To ensure correct flash interface read option, the number of wait states, that is latency, must be correctly configured in the flash underscore ACR, FLASH underscore ACR register according to the flash memory interface frequency. The flash interface implements a dual AXI bus interface for code or data access and an AHB interface for flash interface configuration. The AXI interfaces can request a read or program operation at the same time. So how we do that, I'll show you a table that shows the correspondence between the number of wait states, the bus clock frequency, and the vCore range. This is the table for flash read operation. After power on, the clock used is HSI 64 MHz, and sound wait states are configured by default in flash underscore ACR register. See, corresponding wait states and maximum AXI frequency. See the one in the red, you need to see 0 wait state 70 MHz and 0 wait state 55 megahertz for Vivo S2, and 45 megahertz, which are highlighted in red. So voltage ranges has been given in VCore 1.15 volt to 1.35 volt, and 1.05 volt to 1.15 volt, and for VOS3 that is 0.95 volt to 1.05 volt, and corresponding latencies up to 4 wait states. So the flash interface has a read command buffer. The read mechanism is the following. The read command buffer in depth is fixed to request to 3 requests. When it is full, 3 read requests queued in the buffer. Any new read request will stall the bus interface and consequently the master. Any system read request for data that is not available in the read buffer triggers a flash read operation. This data is buffered inside the read data buffer. If several consecutive read access requests data that belongs to the same flash data word 256 bits. Data is directly read from the current data read buffer and does not trigger additional flash read operations. The read operations are executed in flash interface reception order. So the read request buffer is a free as soon as the last data of the current read transaction is transferred from the flash memory to the read data buffer inside the flash memory interface. So after that the question rises like, what is the error code correction mechanism or ECC mechanism? So data in the flash memory of 266 bits words, that is 10 ECC bits are added per flash word of 256 bits. The ECC mechanism is based on SEC-DED algorithm. It supports single error correction, double error correction. When an error is detected and corrected, the SNECCERR1/2 flag is set in the flash _SR1 or 2 register. An interrupt is generated in the SNECCERRIE, that is interrupt enable bit is set in the flash _CR1 or 2 register. When an ECC error is detected, the address of the failing flash word is saved in the flash _ECC _FA1 or 2 R register. In case of successive error detections, only the address corresponding to the first error will be stored. The register is automatically cleared when the associated flag that generates the error has been set. When 2 errors are detected, the DBECCRR1 or 2 flag is set in the flash _SR1 or 2 register and a bus error is generated. In this case, the received data is not corrected. An interrupt is generated in DBECCERRIE1 or 2 bit is set in the flash _CR1 or 2 registers. So now the question rises, how would I do the cyclic redundancy check? The flash embedded interface embeds a cyclic redundancy check CRC hardware module. This module allows checking the integrity of the flash of a flash area content. This area can be defined either by sectors or by start or end addresses. Only one CRC check operation on bank 1 or 2 can be launched at a time. The CRC operation cannot be concurrent with any option byte change operation. This means that if a CRC operation is requested while an option byte change is ongoing, the option byte change operation must be completed before serving the CRC operation. So the flash interface issues 4, 16, 64 or 256 consecutive flash forward read access. So let's look into that. These transactions are queued into read command buffer together with AXI read request, thus avoiding to deny AXI read commands. The queue command buffer can contain only one CRC command. Okay. So we need simple steps for configuring CRC check, right? The recommended sequence to configure a CRC operation in bank 1 or 2 is as following. Okay. First is enable the CRC feature in the by setting CRC_EN bit in the flash underscore CR1 or 2 register. The program desired data size is CRC_burst field of the flash underscore CCR1 or 2 register. Third is define the flash area on which the CRC has to be computed. Two solutions are possible. Define the area start and end address by programming registers flash underscore CRC SADD1 or 2R and flash underscore CRCE ADD1 or 2R respectively. Or select the targeted sectors by setting the CRC underscore B by underscore sect CRC underscore BY underscore SECT bit in the flash underscore CRCCR1 or 2 register and by programming consecutively the target sector number in the CRC underscore sect field of the flash underscore CRCCR1 or 2 register. Set the add underscore sect bit after each CRC underscore sect programming. Okay. The fourth method is fourth in the sequence is start the CRC operation by setting the start underscore CRC bit. And next sequence is wait until the CRC underscore busy flag is reset. Okay. Sixth is retrieve the CRC result in the flash underscore CRC data R register. So the CRC can be computed for a whole bank by setting the all underscore bank bit in the flash underscore CRCCR1 or 2 registers. Fine. We hear that flash program interface or flash memory interface supports multiple program operations. So what are all the multiple program operations STM32H7 supports? Write to user sectors, erase user sectors, erase bank 1, bank 2 or bank or both. So change user option bytes. The write access is issued through the AXI interface can be considered as bufferable and not cacheable, except that it is not possible to read back the write buffer inside the flash interface. So the embedded flash memory can be programmed using in-circuit programmer or in-application programming. So a program or arrays can be executed on bank 1 while another program or arrays operation is executed on bank 2. So note that the programming parallelism is a parameter that must be configured prior to the performing a program or arrays option. So let's quickly look at configuring the programming parameters. The user application must configure the programming parameters to perform a program or arrays operations in this sequence. One is unlock and program the flash configuration register, that is flash underscore CR1/2, or what I meant is 1 or 2. Set the programming parallelism for each bank through the P size 1 or 2 bits in flash and underscore CR registers. So set the programming delay through the WR write high frequency WRHIGH FREQ parameter in the flash underscore ACR register. Programming operation using time constraint, operation time constraints depends upon the flash interface frequency. So we need to see the flash programming sequence, right? So what are all the steps? I'll give you a simple table for it and then explain it through. So this is the table: simple write sequence, optimal block write sequence. So the simple write sequence for which the steps are: 1. Set the PG1 or 2 bit in the flash underscore CR register of the targeted bank, maybe bank 1 or bank 2. Okay, check the protection of the target memory area. Write one flash word corresponding to the 32 byte data starting at 32 byte aligned address. 4 is check that the QW1 or 2 flags has been raised and wait until it is reset. This sequence can be used to program a block in flash memory. One is set the PG in the flash CR1 and check the protection of the target area memory. Write successively 32 data bytes until the whole block is transferred. Each flash word must start at 32 byte aligned address. So write status busy flags. Have three different status flags located in flash underscore SR1. These were the 3 flags: BSYX, that can be 1 or 2, QW or WBNEX. So BSY flag indicates that an effective write, erase or option byte change operation is ongoing to the flash memory. QW, this flag indicates that a program erase or option byte change operation is pending. This bit remains high until the write operation is complete. So it supersedes the BSY status bit. WBNE, this flag indicates that the write buffer is not empty. WBNE, write buffer is not empty. It is reset as soon as the write command is queued. So if one of the bus busy flags is active, the MCU cannot switch the D1 domain to stop or standby. To release the flash interface, the BSY and QW busy bits must be cleared. Okay. So to release the flash interface, this must be cleared, completing the write buffer with missing data, forcing the write without filling the missing data by setting the FW bit in the flash underscore CR register, terminating the write by resetting PG bit in the flash underscore CR register. This leads to the loss of data in write buffer. So we need to talk about user option bytes, right? After this, so the user option byte change operation can be used to modify the configuration and the protection settings saved as the flash memory option byte area. The flash interface features 2 sets of option byte register. One is the first register set contains the current values of the option bytes. Their names has the underscore CUR extension, current underscore CUR. All underscore CUR registers are read only. Their values are automatically loaded after power on or after an option byte change operation. The second register set allows modifying the option byte, their names containing the PRG extension. All underscore PRG registers can be accessed in read or write mode. So now the big question comes, how the interrupts and what are all the varieties of interrupts that can be generated by the flash memory. So there are four interrupts that can be interrupt event that can be generated by the flash memory. The end of operation, here is the table. End of operation is triggered when one or more flash program or erase operations is completely successful. The programming error interrupt is triggered when a flash memory program or erase operation failed. The write protection error interrupt is triggered when a write access is attempted to a write protected area of the flash memory. The operation error interrupt is triggered when an error is detected during a write operation. So with this we conclude with embedded flash. We have seen in this video about the key features of the flash memory, and then memory flash block diagram, flash memory architecture, flash memory organization, that means bank 1 and bank 2 and the block name and base addresses and sizes, and then flash read operations, which consists of double word, single word, half word, byte, and we have went through a table for range and weight states, AXI frequency in the flash read operations, and then we deeply went into the error code correction, especially SCDED algorithm, which supports both single error and double error detection. And then we went through the CRC, that is cyclic redundancy check operation, and various sequences available or configuration steps for CRC check, and then flash memory program and erase operations, where we discussed in detail about the multiple program operations as well as parallelism and configuring the programming parameters. So flash programming sequence also we went through, and then write status busy flags available, namely BSY, QW, WBNE, and how to make use of it. And then we entered into the user option bytes, and finally we ended up with describing the interrupts available. Thank you for your time. Please subscribe to our channel if you did not subscribe to our channel. For more notifications, press bell icon. If you like this video, please click like button. Thank you.